Okay. So, first tutorial. I've never been to a CIDER tutorial, so I have no idea how this works, but we'll find out together. First thing to know is the tutorial is not located on the virtual machine. You don't need a power cord. You only need a little bit of energy in your computer to do what we're going to do today. So this is not your first virtual machine tutorial. This will be simple. So how do you find what you need? What you need to do is go to the wiki page, which I will do for you. That's this one. Go to Summer Program Tutorials. Click on that. And under Tutorial 1, you will see 1, 2, and 3. And if you want the slides, you can click on 1. If you want a short Word file that describes what we're going to do and some of the questions we're going to try to answer, that's on 2, but you don't actually even need that. What we're going to spend most of our time on is number 3, which is an Excel spreadsheet, a very simple Excel spreadsheet. How many of you have ever done anything with Excel? It's not as bad as you said. You said no one was going to know how to work with Excel. Okay, that's good. So does everybody know how to find the files? Tutorial 2014.
Actually, how do you get it? Can you show?
Oh, man. All hope is already lost.
Because the wiki is ordered really bizarrely.
Sorry? Yeah. Yeah, you can log in with that.
Login is up there. If you like the CIDER 2014 tutorial. Okay.
And if Luis is here, this should not crash the system if everyone tries to download this all at one time because it's not a very big file. Okay? Are we good? Questions? No? You have a problem with everything, though. Come on.
So we download all 3.
If you want. It's like a treasure trove of files. You can have all 3 if you want. Okay.
What is meant by treasure?
Treasure trove. All right. I've never been involved in a CIDER tutorial. I've been told that it sometimes is good to break the students plus postdocs into groups and ignore the instructors, so we will do that. And I've also been told, and I know from experience, that scientists do not self-organize very well. So we're going to go to the 3rd grade phys ed method, and I'm going to request that every student or postdoc in here count off 1, 2, 3, 4, 5. Start over here somewhere. Senior people, forget it. No, you can glom on to whatever looks like the best group. But if you're a student or a postdoc, please count off.
1, 2. And remember your number.
And remember your number.
1.
Come on. We haven't got all day.
Bruce killed it. He died by Bruce.
What happened? You're... This is even worse than I thought.
Just start from the beginning. Go. Ready?
All right, start here.
2, 3, 4, 5.
5. 1. Do I have a 1?
1, 2, 3, 4, 5. 1, 2,
3, 4, 5. 1, 3, 4, 5. 3.
You're not.
No.
If he wants to be a student, he can.
Are we there?
5.
Okay, are we good?
3.
Okay, good. Did you not get one? Pick a number. Okay. And you're now locked into that group for the next 4 weeks. No. Okay. So what I'm going to do is hopefully give you a brief overview of today's topic. And today's topic, as it turns out, is nothing like what was written on the website. It is, but it's similar. It's building a chondritic planet and then segregating so-called siderophile elements into the core and mantle and learning what that may tell us about how the Earth put itself together. So we're going to be looking at measured concentrations of some elements. We're going to be using some real distribution coefficients. And we're going to do a very, very simple model of core segregation that is kind of consistent with what some people believe. And we'll see what we get, and we'll look and try to assess what the strongest constraints on the process are, and whether or not any of the inputs that we put into the spreadsheet actually yield a viable model. And I'll forewarn you, actually none of the conditions that I'm going to give you the data for are actually going to work perfectly. I'm really, believe it or not trying to set up a straw man and convince you that this can't possibly work. Because at the end of this exercise, we want to consider all the things we don't know and still need to be done with regard to models like this. So we're not going to be entirely satisfied at the end of this tutorial, but the final question that I have written on the board is, where would you go from here if you were an experimentalist and you wanted to proceed further on this issue? Ved.
My question is that when I try to download your files, it says 0 KB of question mark. You do not have permission to access the requested resource.
Did anybody else have this problem, or is it just...
It's really designed to block you.
Okay, so the bottom line, too bad. Get with a group that knows what it's doing, okay?
Ben, do you have like a Dropbox I can send you a link?
Okay.
Can you email me?
So the topic, consideration of the origin of highly siderophile elements in Earth's mantle. And I have an alternate title, which is more visceral, and that is exploration of why you don't have to wear hideously ugly plastic jewelry and can instead wear shiny gold if you want to. And I say this with a little bit of a trite nature, but really, if the Earth didn't perform the way that it did with regard to this suite of elements, you could very well be living in a society that doesn't have much in the line of highly siderophile elements. Gold, you could envision, could be easily 1,000 times less prevalent here in the crust where we can mine it than it actually is. And if that were the case, humans probably wouldn't be wearing gold jewelry, and they may not be as technically advanced as we think we are. So just a little bit of practicality to this. Okay, so I'm going to be talking about highly siderophile elements. This is a little bit of a chicken and the egg type question. I'm going to also talk a bit about this on Saturday. So this might have worked a little bit better after the primary lecture, but this will aid us on Saturday as well. So let's get started. The highly siderophile elements, which I may say HSE, include this suite of elements. Let's just go through them. Rhenium, osmium, iridium, ruthenium, platinum, rhodium, palladium, and gold. You've certainly heard of some of those. You may not have heard of some other ones. Ved, this is rhodium. This is ruthenium. He's not very good with element abbreviations, but we can work through that. And the term highly siderophile means these are elements that are really, really strongly partitioned into metal. So where are these elements located in this planet? By and large, about 98% of the Earth's highly siderophile elements are sitting in the core right now. Okay, so this is the paradox, the problem that's involved with highly siderophile elements. This is a beautiful diagram that Liz Cottrell created. I liked it because it's got so much color in it compared to other published figures. But there's lots of figures like this.
That's not a picture of me on the right, just to be clear.
Just to be clear, yes, okay. This is a plot of a bunch of elements that increase in their siderophile element behavior from left to right. And it's a multi-log plot, and their abundances in the mantle are ratioed here or compared here with C1 chondrites, which we'll also treat as bulk earth here. And so the red symbols we'll talk more about on Saturday. They're the so-called moderately siderophile elements. And it's the orange ones that we're considering here today. And the thing to note about them, they are about 200 times lower abundance than they are in a typical chondritic meteorite. And that sounds like they are in low abundance, and they are typical concentration of a highly siderophile element in the mantle is low part per billion or nanogram per gram concentration range. The interesting thing about them, though, is if you go into an experimental lab and you throw some metal into some silicate and you examine the partitioning of one of these trace elements between the metal and the silicate under, let's say, 1 atmosphere conditions, as people were doing 50, 60 years ago, you would find very, very, very low concentrations in the silicate portion of the experiment, the silicate, and these X's in figures like this always represent what the concentration would be if partitioning was like we see under low pressure conditions. And so the paradox, the problem here is that the abundances of the highly siderophile elements by and large are much higher than we would expect from low pressure, relatively low temperature metal silicate partitioning. Okay, and this has been known since the 1950s and 1960s. Now, how do we know the abundances? Well, this is a planet that, as you know, allows us to physically access bits of the mantle. And yes, this is not Liz, but this is a guy holding a big peridotite xenolith from the North China Craton. And so we can go to rocks like that, and we can grind them up, and we can analyze them. And you know what? Bill White gave a talk yesterday discussing the bulk composition of the Earth and some of the controversies in terms of the major element composition of the bulk Earth. There's really not a whole lot of controversy about these abundances. Now, if we got together a group of geochemists that are really only interested in highly siderophile elements, there would be a lot of nitpicking about the absolute abundances in the mantle. But by and large, nobody, do you agree with this, Liz? Nobody really argues these approximate abundances. So this is a set of elements for which we're pretty confident we know the abundances in at least the upper mantle, and if the upper mantle is reasonably well mixed with the lower mantle, we're good to go. I should also point out, in contrast to some of the isotope systems that Bill was talking about yesterday, Bill White was talking about, these are elements that don't like to go into continental crust, and therefore we don't even have to worry much about the effects of continental crustal production. So mass balance, these elements are pretty well understood. There's one other thing that this figure shows, and that is they all plot along kind of a horizontal line, which you notice is kind of the case, but not totally the case for moderately siderophile elements. So that has to be explained by whatever process generated their abundances in the mantle.
That was my question. It looks so suspicious. Also, why do some of them have error bars and other ones don't? And what are the error bars representing?
The error bars represent uncertainties in projections to a bulk silicate earth composition, which I can get into, but you probably really don't want me getting into that. These are tightened up since Liz generated that figure, so I think we know them better than
even the size of the dot on there that's a log scale, so the size of the dot gives you a good factor of 2.
Yeah, in the spreadsheet that you can download, as I'll go to in a minute or two, you'll see bulk silicate earth composition, which again, there would be some minor nitpicking within the geochemical community about it, but by and large, yeah, yeah, hasn't changed. It's not going to change. It's not going to change. Okay? Now, embedded within this suite of elements are two radiogenic isotope systems, and we're going to work with those a bit today. And one is one of my favorites, which is based on the decay of rhenium-187 to osmium-187. Both of these elements are highly siderophile elements, so they were among the orange symbols there. And this is how we believe the mantle has evolved. Okay? There is finite uncertainty in chondritic evolution. We can talk about that later on. But by and large, what we're going to look at in our calculations later on, if this were to actually work, there we go. If we fractionate, vary the rhenium-osmium ratio within the mantle by even a small amount, long ago when these elements were placed into the mantle, we might get evolution along a trajectory like this or like this. And we will see differences, therefore, in the modern-day isotopic composition that we project from the models that we're going to run today. Okay? We have one other system, which is a nightmare system in some ways. It's platinum-190 decays to osmium-186. It's an alpha decay system. It has a I didn't say before, but the rhenium-187 has a half-life of about 42 billion years. This system has a half-life of 450 billion years, and the parent isotope is a very minor isotope. And so this is a isotope system that is exceedingly sluggish. You can see we've got several more significant figures here, and we can do the same thing and see if the ratio in the mantle is actually higher than chondritic, it might evolve up that way. If it's lower than chondritic, it might evolve off that way. And so we'll do that. And the good news is, in the spreadsheet, I did all the calculations for you. So you only have to think about the results. You don't have to deal with the Excel spreadsheet other than putting a few numbers in case you're getting worried. Are you getting worried?
No, I still haven't downloaded it.
Oh, dear.
Well, the internet sucks. Yeah. No.
Okay. Well, while Ved continues to work, I can give it to you on a disk. Anyway, so how did these elements get into the mantle? That is the question that we want to address in part today. Over the years, there have been three broad hypotheses tendered to explain the abundances of the highly siderophile elements. Why those orange symbols plot where they do on that diagram. And one of them has been termed inefficient core separation, which I'll show you what it is in just a second, but it's just what it sounds like. Segregate a core but leave some of the metal behind. Number two, a process called late accretion. And number three, what we're going to be considering today is metal silicate segregation at highly elevated pressures and temperatures. Some people call it magma ocean hypothesis. Okay? So the idea of inefficient core formation is you're building a planet, you're adding stuff perhaps to a partially differentiated body. Some of the metal, which is shown here as little red droplets, may stick around in the mantle. Ooh, that doesn't look too good here, but ultimately you end segregation of metal from the mantle, and you've left some portion of metal behind, and ultimately for it to end up looking like the mantle today, you've got to oxidize part of it and make the metal go away. Any problems with that idea? This idea was kind of generated maybe 30 to 40 years ago. It was before people were thinking much in terms of magma oceans. This is a model that I think still has some utility, but it's hard to envision much metal sticking around in a planet that is periodically experiencing magma oceans. So not much has been done with inefficient core formation in about 3 decades. The second idea, which I'll talk more about on Saturday, and is my favored candidate for this, but it's by no means proven, is late accretion. And that's a concept where you form the Earth, you segregate the core. At some point, core segregation ends. Ooh, these just didn't come out very well in projection here. And then you add some chondritic material to the silicate portion of the Earth, buffering up the concentrations of these elements, and defining the mantle then as having chondritic relative abundances of these elements. The idea is if you're impacting differentiated bodies, none of the metal from those get into the core, and they have the same problem that the inefficient core segregation model has, which is you have to ultimately oxidize the metal to have it go away. Because we don't find metal in the mantle today, right? Good, okay. And what we're going to consider today is a lively topic of conversation in the community, and that is metal silicate equilibration at high pressures and temperatures. I'm not going to say much about it today, but I think it's relatively safe to say that the community that works on these issues generally agrees that the moderately siderophile elements, the red elements in the earlier slide, were probably set by a process like this. And Bill mentioned this as well yesterday. So the idea is you have a body that is segregating a core, but you may have a molten exterior, a magma ocean, and you might have pooling of metal at the bottom of the magma ocean. And the idea is at these depths, you're doing the equilibration between the metal and the silicate, and that's what defines the final abundance of these elements in the silicate portion of the planet. The metal ultimately drops diapirically through a solidified lower mantle into the core. Okay? So again, to reiterate, people generally agree, they have different models, but geochemical world that works on this generally agrees that the moderately siderophile elements were established by this process. So it's not probably as simple as this. The Earth perhaps went through multiple magma ocean stages, but some average pressure and temperature was probably established, which ruled the partitioning. Okay, so what we're doing today, we're going to build Earth from materials with C1 chondritic bulk composition. We're going to determine HSE abundances and osmium isotopic compositions of the mantle if they were established exclusively by metal silicate partitioning at high pressures and temperatures. Okay, we're also going to do a little bit of varying of another factor, oxygen fugacity, but that just stems from the source of the distribution coefficient data that we'll be using. And so we're going to assess whether the model results for any conditions resemble the modern mantle. Again, I tell you, none of them are going to be perfect. Most of them don't come close, but it'll allow you to see what would have to change in order for this type of model to work. Okay? Okay. Bill White yesterday actually did most of the work here. So a few words about trace element modeling in the system we're about to deal with. The highly siderophile elements are to be treated as trace elements. And in many geological scenarios, we can use measured distribution coefficient in order to quantitatively predict how these elements should partition between different phases. In this case, our interest is in looking at the partitioning of this suite of trace elements between a molten silicate Earth and metallic core material. Okay, and again, yesterday this term was defined, a capital D. We're not going to go into differential equations here. We have very simple equations. D is bulk distribution coefficient, and it is just simply a concentration ratio between two phases. In this case, the two phases, again, are metal and silicate, liquid metal and liquid silicate. And so here's the relation. That's not too bad, right? Okay. And For this case, what you're normally treated to in a textbook would normally be presented like Bill presented it yesterday, where we have C sub S is the concentration in the solid and C sub L is the concentration in the liquid. And then you go into a mass balance calculation or equation like this, which Bill showed you yesterday. The C sub O in this case is the concentration in the starting system. What would that be for our planet? It would be the bulk composition of the planet. So it's our chondritic composition. And in this case, in the equation, F will represent the mass proportion of the silicate Earth, which is what? Come on. What is the mass proportion of the mantle in this planet? Oh, I'm going to go home. It's about...
What's the inverse? What's the mass proportion of the core?
I can do that. I'm not going to go forward until we get an answer.
You should call on someone, but not me.
37.
Okay, I'll tell you. It's about 33% of the Earth by mass is the core, and 67% by mass is the mantle. If you learn nothing else at CIDER 2014, that's a good one to know, okay? All right, again, Bill went through this yesterday, so I don't have to do it again. This is actually the equation that's going to go in one of the Excel spreadsheet cells that we deal with. The only question, and again, this is a useful equation for a system that is in equilibrium. Now, geochemists use lots of different equations to model trace elements. This is a really, really simple one. It's probably not really applicable to this problem, but you know what? It's also probably not going to give us a result that would vary all that much from a much more sophisticated approach. So we're going to go with this. This is something you can look in the cell. You'll see these terms and be very easy to understand where they came from. Okay, and again, this is the type of figure that you normally see in a geochemistry textbook. So this is concentration in the liquid ratio to the concentration in the starting system for incompatible and compatible trace elements. Are our highly siderophile elements considered to be compatible or incompatible? Well, that depends what you define as being the CS or the CL here. In the equation that we're going to use, we're going to be looking at metal silicate partitioning. And so the distribution coefficients that we will be applying are very large, by and large, and therefore these are elements that in the system we'll be considering are highly compatible. So here's a D value of 10. In some cases we'll be dealing with D values of 10 to the 7. So you can see this relationship here. As you approach a very small proportion of mantle, you approach a concentration ratio of 1 over D. But you'll see that even for an F of 0.67, we're going to see very low concentrations. And that's consistent with what we see in the mantle. We do have low concentrations of highly siderophile elements in the mantle. Okay, so that's the theoretical background. Now, a few other words before we get on with this. Where do distribution coefficients come from? Unfortunately, they are not handed down to us on golden tablets from heaven, and that's really unfortunate. They really come to us in fundamentally one of two ways. Natural systems, we can look at, in some silicate systems, phenocryst glass ratios. In some meteorites, we can look at metal silicate ratios. But this is the way most of the ones that we will look at come from, and that is experimentally. And just a few words about experiments. This is what an experiment looks like when you complete it and you saw it open and you look at it. And we have one of the experts on this subject, Liz Cottrell, right here. And what these guys did, Mann et al., which is the paper that we're going to be drawing our data from, they put some metal and they put some silicate into a MgO single crystal capsule, and they pumped the system up to varying pressures and temperatures and let it equilibrate, and then they quenched it, and then they analyzed the metal and the silicate for the concentrations of the highly siderophile elements in it. And since a D value is a concentration ratio, you just get a D value from that. Sounds really simple. Is it really simple?
Well, I mean, they can see from the figure, perhaps you guys can see from the figure how complicated it might be to make that analysis. How do you analyze the silicate phase of quenched crystals? How do you average that? How do you derive the concentration? So it's how do you know what pressure you were at or temperature, all these numbers. But yes, data, partition coefficients come out of these experiments in our reporting in the literature.
So measuring their abundances in the metal is easy.
The oxygen fugacity is really critical to HSE partitioning, as I'm sure Bill will.
Right. And we won't talk about it here, but a real big issue that has plagued people that do these types of experiments is you oftentimes, at the end of the experiment, when it's quenched, you find little tiny micro nuggets of the highly siderophile elements in the silicate. And the question is, do you include those in your concentration measurement of the silicate, meaning they exsolved from the silicate melt at the time it was quenched, or were those just little bits of metal floating around in the silicate during the experiment, in which case you wouldn't want to include them. So it's a complex issue, which I don't do, and any questions you might have should be directed at Liz, but go ahead, you can try.
I just have a quick question.
Here.
Like quantitatively, how large are the uncertainties on these partition coefficients? Like how much wiggle room do they
We're
give you?
going to look. We're going to see that. You're going to get to insert different numbers into the spreadsheet.
Okay.
So you will soon have a feel for that, a very good feel for that. Okay. So what else is varied? Pressure, temperature. This paper, they varied oxygen fugacity. And so the three variables that are present in the data that we'll be working with are pressure, temperature, and oxygen fugacity. Liz, are they all unrelated? Can you just dial up any pressure, temperature, oxygen fugacity you want? In 3 words or less?
In these data sets, pressure and temperature are often involved because the higher you go in pressure in your experiment, the higher temperature you need to go to melt the silicate. So in large data sets that go over many, through pressure steps and transition zones, you'll see that pressure and temperature are difficult to disentangle as independent variables. Oxygen fugacity is more of a let's measure what we got after the fact. Then I would not say that in any high pressure experiments oxygen fugacity is controlled. It is we try to assess it after the fact. 1 atmosphere experiments, the oxygen fugacity is controlled and known with great certainty. In these experiments, the uncertainties are large, and there was no control. There was only kind of detective work after the fact.
Okay, you asked about uncertainties. This is the actual table from the paper that we're working with. Why are we working with this 2012 paper? Well, it's useful because this group did a bunch of measurements of different highly siderophile elements, all in the same set of experiments. And so we have data for a bunch of different elements, again, processed under the same conditions. You will see little plus or minuses. So these are the uncertainties associated with it. These data I have put into the second page of the Excel spreadsheet, and these are the things that you're going to vary in your groups to see what their effect is on concentration. Yes, Liz?
You're going to talk at all about like a measured partition coefficient?
No.
Like inverse element one?
No, I'm just going to continue with these and see what happens. Okay, so I call this a dazzling array of metal silicate D values. We are just going to apply them directly. I will notice here, or I will have you notice, they go, here's the different pressures, 3.5 gigapascals up to 18 gigapascals. We're going to go to 40 and 60 gigapascals. And they didn't actually measure distribution coefficients at those conditions. They extrapolated up to them, and that's something that's worth keeping in mind. Why don't they just simply do these experiments at 40, 60, 80, 100 gigapascal? Not so easy. So the higher the temperatures and pressures, the more difficult the experiment. And usually the smaller the charge. So we can do, when I say we, it's not me, but people can do diamond anvil cell work, as I'm sure we'll hear something about that here, to very high pressures and temperatures, but they produce very, very small experimental charges. And we need a lot of atoms to make these measurements, especially if you have a really high distribution coefficient. So this is really hard work. And so a point that I want to make is the D values that are shown here are not handed down from the heavens above. They are for specific conditions, for specific compositions. They did the measurements in certain ways. It by no means is the only way you could do this. Yes?
Typically, the uncertainties here look like they're 10 to 40%, but sometimes they exceed the value of the distribution coefficient.
What are you saying?
Well, I'm asking for a comment.
I'll
The
let.
uncertainties are quite large, right?
Yeah, and those are probably, those are probably just their, I hate to tell you, but those are probably just their measurement uncertainties. Taking these partition coefficients and applying them to the Earth requires, there's an assumption of Henry's law, there's an activity composition correction, and that's the whole kettle of fish and the extrapolations in PT space. So these are just probably measurement uncertainties.
There was another question?
What I don't understand is, if you look at these, and maybe this is the point of the tutorial, but if you look at these coefficients for the different elements at the same conditions, they're different.
Well, but they're all different conditions.
No, so if you look at a single row.
The oxygen gasity too bad.
No, it's the same row.
Well, these are different elements.
Yes, all the elements are different. That's what
Yes.
I said. So, but when you look at that line, they're all the same. That's what we measured, that they all have the same concentration.
That's what we're going to model. We're going to try to duplicate that.
But then, what? I don't understand, because
You're just so smart that you've gotten to one of the points of the exercise, probably. So
Yeah.
just wait.
I'm not.
Okay. Anyway, so we're going back to this. This is a figure from Wade and Wood, a 2005 paper that everyone likes to use. So again, just to reiterate, we're going to be looking at partitioning between metal and silicate as you might envision at the base of a magma ocean or a series of magma oceans. If you really wanted to model this in a robust way, you would work with a planetary dynamicist, and you would build the Earth stochastically, and you would want to model the partitioning as a function of Earth growth. And I'll show you a figure on Saturday where people have done that. That's something that Wade and Wood have actually done. But by and large, this is what we're about to model. Okay. So we're not doing CSCl. We're doing C metal or core and C mantle. So I've just modified the equation a bit. This is ultimately what is in the cell that calculates the concentration of the highly siderophile elements that result from trace element modeling in the mantle. And how would you calculate the core concentration? Well, if this is truly equilibrium, it's a really simple equation. We said that the concentration in the metal over the concentration in the silicate is equal to the distribution coefficient, so it's pretty easy to calculate the corresponding core. One of the things that you'll want to notice is anything happening to the core? We're changing partition coefficients. How does that affect the core? Does it affect the core at all? Of course it affects it some, but we'll see. Okay, the last thing before we get started is isotopics. I'm not going to make isotope geochemists out of you. That's sad, but...
Yeah, you should.
Yeah, I know I should, but I won't. So one of the things we want to do is once we have created a mantle 4.5 some billion years ago with the highly siderophile element abundances that we calculate, what are the implications for isotopic evolution for the next 4.5 billion years? And it's a relatively simple calculation. We use an equation like this. This would be the osmium isotopic composition today. This is something that we measure in the mantle. Again, geochemists nitpick about what the osmium isotopic composition, 187 isotopic composition of the mantle is today, but not a whole lot, not enough to talk about here. This is the solar system initial ratio. This was the ratio that we get from meteorites, plus, well, this is calculated from the rhenium-osmium ratio that we get in the mantle. And here I have to say, I have to apologize. Mann et al., the paper that I'm taking the distribution coefficients from, did not include osmium in their experiments. Why did they do that, Liz?
Why did they not do that?
Yes. It's a hell
It's really
of an element.
toxic and difficult to work with.
We don't care about toxicity, but
You don't care about toxicity.
nah.
Whatever gives you an answer.
Yeah.
Is there another answer?
No, but instead we're going to use a near geochemical twin, and that is iridium. So you'll notice in the spreadsheet I'm just using the same distribution coefficient for osmium as they measured for iridium. One of the criticisms of this type of modeling then would be we don't actually have actual distribution coefficients for osmium under the same conditions.
So why did you use osmium partition coefficients for different studies?
I wanted to keep everything from, I wanted to keep the comparison. Yes.
How different is this assumption of iridium from measured values in other studies?
I can't answer that in 3 words or less. Everybody runs things under different conditions, so it's not that easy to make a comparison. But I don't think they're wildly different. This is just a fun exercise, folks. Okay. And then finally, osmium 186, same thing. We measure platinum, and we measure osmium, and see how this system evolves to the present. Okay, so that's all I have to say. I just want to show you the spreadsheet and give you a really quick overview of it. So this is what it looks like. Hopefully you have something like this on your computer. Just as a quick aside, these are the bulk Earth values we get from C1 chondrites. C1 chondrites actually aren't a particularly good fit to the Earth from a highly siderophile element standpoint. We can discuss why that is later on. Bulk silicate Earth or primitive mantle concentrations are shown here with their estimated uncertainties. This column labeled D value, this is what you want to vary. Very simple. If you look at the box, it refers to the next page of D values. All you need to do is change that final digit or final 2 digits in this box to change the distribution coefficient to the set of conditions that you'll be assigned. The spreadsheet will calculate concentrations for you in nanograms per gram in the resulting mantle and in the resulting core. So pay attention and see if anything changes as you change distribution coefficients. Geochemists like to normalize things, as we learned yesterday. So we're going to normalize the results to chondritic, and that's what these 3 columns are. And down here, I've even got it plotted for you. Isn't that nice? It is. So you can, yes? I had to get my wife to get me, to show me how to do that. I don't actually know how to do that. Yes?
I was wondering if you could talk just a little bit about when we look at the FO2 numbers, what we should, just a reminder of which we should take as most relevant for the surface and the mantle.
Core formation is often modeled, but that's one of the questions that one of the reasons one does these studies is to figure out the likely
Oh, sorry. This will work.
One of the reasons for doing these experiments is to do this kind of modeling to determine the likely oxygen fugacities relevant for core formation. But based on the iron content of the mantle, we typically think of core formation as having occurred at iron wustite -2, if that means anything to you. So 2 orders of magnitude below the equilibrium between iron metal and wustite FeO at any given P and T.
So we don't have any that are actually this low on our list, and we have some ranging from minus around 1.5 to positive 1.5.
Because they're trying to probably avoid the micro nugget issue, which is an experimental problem.
Plague.
And because, like I said, it's difficult to control the oxygen fugacity, and so that's just how the experiments came out, and why one experiment comes out one way and another comes out another is not always easily understood.
Michael?
I don't think anyone has defined oxygen fugacity.
What? Should I just mic
you
myself
can,
up?
sure.
So I'll
do the isotopic
I'm going to do that on Friday, but oxygen fugacity can be thought of. The oxygen fugacity in this room is 0.21. It's the oxygen partial pressure in an ideal gas. Partial pressure and partial pressure and fugacity would be the same, would be equal in an ideal gas, an ideal solution of ideal gases, but we don't have that, so we add the fugacity to indicate, to account for non-ideality. So fugacity stands for like fudge factor, if you will, and so rock is certainly not an ideal gas, and so since rocks are not ideal gases, it's oxygen fugacity, but you can think of it in thermodynamic terms, it's the activity or the chemical potential of oxygen in the system, which is just what partial pressure is. So that's oxygen fugacity.
Effective partial pressure is a way to think of it.
Okay.
Yeah, the activity. It's the activity.
It's not like there's oxygen that's hanging out waiting around, right? And so
It's not free oxygen.
Right.
And so it's the availability of oxygen to participate in chemical reactions. You can actually have a lot of oxygen. The mantle is 44% oxygen, but relatively reducing relative to the surface environment because the oxygen is not free to participate in chemical reactions and oxidize other species.
Okay, we need to move on, but quick.
Yeah, just for clarity, these experiments were done with pure iron, right? So they were not done with a sulfur.
Impossible.
Oxygen, of course, because of the equilibration, but they weren't done with any sulfur, argon, or silicon, which could, if there's any complexation between any of those elements and
Sure.
your HSEs, could mess up these partition coefficients.
You're getting to the final end state question that we want to think about, which is...
The metal surely has all of those dissolved in it, though, because it's in equilibrium with a silicate melt.
But did they have sulfur that are charged? I bet they did.
No, but you said silicon, for example, oxygen, carbon are all unavoidable in the metal.
I doubt they included carbon as charges.
It doesn't matter if they added it deliberately or not.
Yeah, but you're not going to get to
Right. No, right. They're not done in graphite, but silicon will be in there for sure.
Okay, just keep thinking. This is a simple calculation we're doing. Mm-hmm. So the last thing I want to say before turning you loose, sorry this has taken so long, is isotopic evolution. This is done for you. So we take the rhenium-osmium and platinum-osmium ratios that result from the partitioning calculations. They get plugged into these 2 yellow cells. Actually, the results get plugged into all 6 of these cells. But these yellow cells represent the isotopic composition of the mantle after 4.6 billion years of evolution with that ratio. What does that mean? Well, in this case, and I think in this case I have the lowest pressure experiment embedded in the D values for the spreadsheet I'm showing you here. This would give us a present-day osmium isotopic composition of 2.34, which means nothing to you, but you can compare that with our bulk silicate earth or primitive mantle estimate for today, which is about 0.13. Does that sound similar? It does not. So this result is wildly different. Here's osmium 186. You have to look at a few more significant figures to grasp the meaning of this. This is 0.12060. The present day measured value of the mantle is 0.119834. Notice the uncertainty in this is pretty far over to the right. So this is a failed model as it is. And you can see that down here in the figure. What you want to do is, this is the bulk Earth. That's not going to change whatever you change in the spreadsheet. The green represents the resulting mantle. You can see the osmium and iridium are the same because we're using the same distribution coefficients. This is the core. So the abundances that we generated by this low pressure experiment are way, way, way below where the mantle is today. And also, as we just saw, the isotopic compositions are very different. Okay, so it's not going to take you long to put the different your groups, not you specifically, but somebody's going to have to do this, to put different distribution coefficients in the... Ooh, do we have a way of blocking this off without turning it off? Huh? Standby, does that do it? Oh. Uh-oh, uh-oh. No, I don't want to do that.
Put your PowerPoint back on hit B.
Hit B?
But run the show first.
Really? Is that going to solve it? Oh, very good. Okay. So, here's the questions you really want to think about as you do this. We'll divide up into our groups. Here are your groups. The groups 1, 2, 3, 4, 5. These represent the different conditions on that second page of the sorry, I could have written bigger. On the second page of the spreadsheet, they represent different lines. So I have the line number. So you really just need to change the final 2 digits in the D column in order to embed the correct distribution coefficients. So this is not the interesting part of the exercise. So just each of these groups should do at least 3, but you're welcome to do as many as you want. Look at what pops out the other end. So you'll look at the highly siderophile element patterns, look at the isotopic composition that result from that, and then consider these questions. And I don't know what I want to do this for, but we'll come back maybe after, we'll go until 3:30, go to the coffee break and come back for about 20 minutes to discuss, something like that. So here they are. Results of, gosh, that's not grammatically correct, is it? Results of model with, in comparison to bulk silicate Earth. I've already told you the answer to that, which is none of these are going to be particularly good matches to it. But what's wrong with them? What are the particularly offensive elements? Do any of the elements work? Okay. Number 2, isotopic results. Do any of the isotopic systems work? Do we get something approximating what the modern mantle is with any of the conditions that are incorporated into that second page of spreadsheets? Whoa, this is where it gets a little more exciting. Uncertainty propagation. Does it matter? People back here are a little bit concerned about very large error bars. Does it make a difference if there is essentially an order of magnitude error bar? Try it. How would you go about doing that? Simplest way would just be make the number as big as the error bar permits, make the number as small as the error bar permits, and see what that does to the calculation. That's not the elegant way of doing error propagation, but it gets you pretty close to what you want. So again, the question is, does it matter? Other body predictions. I don't know if we'll have time, if you have time to go through this, but what are the predictions for other planetary bodies if they experience magma oceans? The Moon, Mercury, Mars have very different sized cores. Moon about 2%, Mercury about 80%, Mars about 20%. If you had the same applicable distribution coefficients and you chose the right conditions, what would you expect to get in the mantles of Moon, Mars, and Mercury? D-value constraints. You can turn this around. You can say, what kind of D-values would I need in order to generate the necessary isotopic compositions that we see, and how variable can they be in order to still retain the isotopic compositions that we see. How would you approach that? You can just plug any numbers you want into the d values until you get matches with the isotopic composition. See how much variability you can have in order to generate the isotopic compositions that we see today. And then we run into this issue. Again, I don't know if we'll have time to talk about it. Problems with results. You know, somebody with a great experimental background, Liz, did some experiments. When was your PhD published?
2004.
So about 10 years ago, she did some phenomenal work on platinum, the element platinum. And she got, I think, pretty similar results to what we're seeing with the Mann et al. Results. I don't think there's a dramatic difference. Does that create a problem for us? And by that, what if you can match the platinum concentration in the bulk silicate earth by magma ocean partitioning, but an element like osmium you can't? Is there a way around that? I don't know. And then you can think about flaws in the assumptions. And then number 7 is where best to focus future research. If you wanted to work on this problem, what would you do next? Okay, so I suggest group 1 meet up here somewhere, group 2 back there somewhere, group 3 there, group 4 over here, and group 5, if we get these lazy people out of the front row, could meet over here. We'll have Bill White and myself assist, correct?
Yes.
You look troubled. You
Yeah,
look.
but it doesn't look like any, you get a slight error, you see that A.
Oh, I don't have that.
Both Bill and I do.
Really?
Yeah, everybody else does.
So, I mean, the A is just tell people to get rid of the A, I'm sure, and that will work, right? 2.8.
Oh. So in cell A25, or is that right? L25, there's an A in front of the number. You should remove the A. I don't think I have that.
In the avionic, we got screwed up somehow.
Ah, there it is. You are correct. Sorry about that.
Also, you have an extra line on the platinum data set. I don't understand that.
Sorry, where?
Go to the platinum data set. Go to the far end.
The highly siderophile element abundances in the mantle as a consequence of varying pressure. So I told you at the outset you would fail, but we hopefully learned something from our failure. And so now let's consider some of the questions. We just answered question 1, so I don't think we need to discuss that further unless some group actually got results that worked. Did anybody? I didn't get a sense that anybody was. Ved, did you?
I guess we make up coefficients.
Yeah, you can make up coefficients. Okay, so we need to get on so that we're finished by 4:30. So none of these models, using these experimental results, produced a bulk silicate earth like we think we have. Okay, number 2. Go ahead.
Except that, to be fair, that as they go up in the pressure, they're approaching that value.
They are approaching.
Yeah.
That's certainly true. And again, I just want to keep emphasizing, every time I walk by a group, I emphasize that the people that have worked on moderately siderophile elements are generally convinced that those elements were primarily established by magma ocean processes. Most of those models are typically in the 40 to 60 GPa range. So one of the questions to think about, and I don't think we have an answer to this here, is if it works for moderately siderophile elements, and it works for some of the elements that we're seeing here, like palladium, how do we explain the other elements? And that's a conundrum that I don't have an answer to. It's something that I worry about, but I don't have an answer to it. Almost by definition, you didn't get the correct isotopic results using any of the conditions. Did anybody get anywhere close to the observed isotopic compositions? Yep. What conditions?
It's with a bunch of forced distribution coefficients.
That's okay. Forced. I like that.
Basically make it the measure composition. You get the platinum osmium system with an error of what we measured from Mantle.
So this is getting on to 5. Did you do an iterative calculation to see how much you had to vary bulk distribution coefficients to keep it within the range of bulk silicator? Did anybody do that? Well, that's something we can do on a rainy day if we have nothing better to do. Okay. What did the uncertainties do? The Michael Manga question. He was worried about the big error bars, which are probably underestimates of error. Did they have a major role here? What's the conclusion? Group 1?
Yeah,
they did.
So, we tried plugging in the d-values for 16 GPA,
Uh-huh.
and then we sort of fudged the uncertainties in there.
Yeah?
And some of the matches are pretty close.
So you got pretty good results. That's not too bad. Hold that up. Everybody applaud.
So the fudge factors are...
Wait a minute. You didn't say fudge factors. You just said errors. You expanded to the stated errors, right? You certainly didn't...
We have to go beyond.
Oh, no.
Only for 4 of them, yeah.
That's... Okay, so group 1 is the group of cheaters. Now we know that. No, I'm just kidding.
What are your isotopic ratios that you get? Did they work?
The 186, 188 is 0.119836.
That's pretty good. That's pretty good.
The other one is 0.1432.
Okay, so one way of improving the situation in the future, if there are technological breakthroughs, would be making the measurements and generating or running the experiments and being able to make the measurements to higher precision to reduce the size of those error bars. You had to fudge it by a factor of 100. That's a pretty big fudge, even in the world of geochemistry. Okay. Yeah. Okay. So the answer to this, I think if you didn't fudge it, you might say it really does matter then, or it doesn't matter. A factor of 100, that's a pretty big fudge.
Factor of 2 helps.
Factor of 2 helps. Okay.
It's off by a factor of 50.
Yeah. Okay, did anybody group 2 back here? What exciting discoveries did you make? This is the shy group.
We didn't go anywhere near as far along as what you just heard. Just, working within the range of errors.
Here, where's the microphone?
Right here.
Do we have one in?
Okay, yeah. So we didn't go as far along, but looking at the errors that were in the second spreadsheet, we could get the daughter ratios to be close.
Mm-hmm.
But that's just for osmium. We didn't look at the other ones quite as closely.
So could you match the isotopic composition but not the concentrations? Is that what you're saying?
Right.
Okay. Anybody else able to do that? Here.
Oh, and I'd like to use match loosely.
What's that?
Consider match to be loose.
Loose match, but there were actual error bars in those ratios. Are you just ignoring those actual error bars? Which group are you? You're group 3?
No, still part of group 2. So we were only varying pressure in ours, and so it was interesting to see that we were getting closer and closer to the bulk silicate earth with our by upping the pressure, but the platinum overshot. So that was an interesting point that we discussed with you, was that even though we are getting closer on many of the elements, because platinum overshoots what we're aiming for the bulk silicate earth, pressure isn't the only variable that we have to play with. And so I want to add that.
So an overshoot is a problem.
Sorry, palladium, not platinum. Palladium.
Platinum gets up there too. So, but palladium is the most offensive of the ones in this set of distribution coefficients. How did group 3 do? Group 3, report, please.
We found that we didn't really get anywhere near it by varying the oxygen fugacity at 6 GPa. However, for the highest...
So is that saying different oxygen fugacities didn't affect it much?
It did affect it, but none of the values that we were given were anywhere close to the bulk silicate earth or the osmium ratios. The best one was the highest oxygen fugacity of 0.56, and we found that if you use the lower bounds of error, you can make the osmium and iridium match for the bulk silicate earth. You can find a value within the error that does match, but none of the other ones are even close. So that's the best we got.
Okay, thanks. Group 4?
We kind of, well, some of the person maybe already reported first. Yeah, same sort of thing. So we can fudge it to get it, but not anywhere near the orders of magnitude away from the partition coefficients that have been measured. So yeah, and you can play tricks like sort of varying, as you did, varying the sort of parent-daughter ratios to try and match the isotopes. But you are playing. It's not necessarily based on any of the measurements we have.
Yeah, but you can turn that around, and again, if you want to match the isotopic composition, you can see how much or how little you can change the distribution coefficients to match the observed data, and you can come to conclusions on how much variance you can have in the distribution coefficients. They usually end up much tighter constraints than experimental systems can match. The uncertainties in most experimental measurements like that are usually much larger than would be allowed from the variance in the data. Bet.
I have a kind of, I don't know if it's a pseudoscience or philosophical question, but why would it be that the Earth, you have these concentrations that are all the same on that plot, right? And then we fudge these partition coefficients to make this come out of something that doesn't look anything like that. Why would that coincidence take place? Is there any ab initio reason to believe that these elements would actually partition in the way that's required to reproduce a constant concentration across the whole?
I'm not qualified to answer that question. Liz or Anat?
It just seems so perverse.
Perverse? I don't think that's the
reason, the initial motivation for a lot of the research was that this Murphy paper that was alluded to, the idea that in a magma ocean, as things get really hot and the liquid metal and the liquid silicate approach supercritical behavior, as the liquid silicate and the liquid metal become more and more similar, all D's, all partition coefficients will converge to 1. And so the original ideas about why a magma ocean might satisfy the siderophile element problem, which as originally formulated wasn't so focused on the platinum group elements or the highly siderophile elements, was focused on Ringwood's observation that the 1 atmosphere partition coefficients can reproduce the moderately siderophile element abundances. And then this idea that you have a really hot planet and a hot magma ocean causing the partition coefficients to become more similar. And then the fact that when this went to be investigated with it, people looked at highly siderophile elements and they do converge. It does follow the thermodynamic predictions you make. So that's I don't know if you said it's perverse. I don't know if it's perverse, but that was the idea, I think, of why people thought that magma ocean conditions might cause these partition coefficients to converge.
But if we had all those partition coefficients equal, we wouldn't reproduce that, would we?
Yeah, you would get that's required. So group 5, how did we do? What did you learn? Group 5.
Very much the same thing as everybody else.
Oh, come on, something new? Do you have something new to add? You had, on average, the highest pressures, so 18, 40, and 60. So you certainly would have had the same outcome as group 4 for 60. And presumably palladium excess, yes?
Yes, palladium in excess. The result is pretty much the plot that we saw on the Excel figure. I mean, we note that all of that figure that they show, they give a constant FO2 of iron wastate -3, which is lower than any of the data points that they have in the spreadsheet at all. But FO2 goes in the wrong direction to help us with this problem. That's taking the worst case.
So does Group 5 think that that's a problem? I mean, if we get to the final question, where to focus future research, if you, heaven forbid, decided you wanted to work on this problem, is that an area that would be appropriate, trying to change FO2 conditions?
It doesn't look like it's going to solve the problem.
Okay.
But it's true that it hasn't been tested.
Okay. Okay. And I know we're running out of time, but I know a few groups. We talked a little bit about predictions for other planetary bodies. Anybody want to comment on that? They have different mantle to core size, mantle to core ratios, very dramatically different, from about 2% core for the Moon to 80% for Mercury. Would this have a major effect on highly siderophile element abundances? All things being equal, you of course would be partitioning at probably very different pressures for Earth and temperatures, probably different temperatures, and then you would have the proportional difference in the size of the silicate reservoir. But that would have a relatively modest impact on the final concentrations, I think, if you plug different numbers in. You guys did that. What did you find? You plug in a low number, a high number. How much does that vary the concentration? Well, I'm not asking if it's better or worse. How much does it change it? This would be a prediction for... Yep.
It just basically shifts up or down.
Yeah. It doesn't change the pattern shape. Right. Okay, but that would maybe suggest if you went to Mars and you got some mantle samples, and you went to the Moon and got some mantle samples, and you went to Mercury and got some mantle samples, if this suite of elements were all set by the same type of process under different conditions, you would expect different concentrations, correct? Probably. And what I told some of the groups is we actually think we know the highly siderophile element content of the lunar mantle and the Martian mantle. And amazingly enough, the Martian mantle looks frighteningly similar to the terrestrial mantle, which is a problem. It's a problem for me. And the Moon looks quite different. In both planetary bodies, it looks like the highly siderophile elements are in chondritic relative proportion. And that's based on the fact that both the Moon and Mars have probably chondritic osmium positions today. So that assumption then based on ratio of 2 elements over solar system history. The Moon has much lower highly siderophile element abundances in its mantle than the Earth, which is an interesting observation. Okay, so flaws in assumptions. I think we've talked about that in the different groups, but there's lots of problems, one of which we're using fictive osmium partitioning data. That's a bit of a problem. So if we were to redo this and we had an unlimited budget, we might want to somehow work really hard to get osmium into the experiment, because it's very important as an isotopic constraint. But it's a very difficult element experimentally. What else would we want to do if we had an unlimited research budget and we're really interested in this? Liz, you practically have an unlimited research budget, and you are interested in this problem.
I think that a lot of effort should be invested in doing experiments at pressures relevant for a magma ocean. The data up to 25 GPa seem, for moderately siderophile elements, seem to converge or make predictions about magma ocean conditions, but everything at 60 GPa is an extrapolation. We were just talking about papers that have come out with showing a big kink in the partitioning, the effective pressure on partitioning, that would say that you can't extrapolate from below 25 gigapascals up to, say, 60 gigapascals. But what I pointed out is the big break in slope occurs where you have a change in the type of apparatus the experiments are done in.
That's just coincidence.
And this is also true. The too big kink at 2 gigapascals. It's the break in slope happens going from piston cylinder to multi-antle, and at 25 GPa you go from multi-antle to diamond cell. And so I think we should be very suspicious that these large changes in the function for pressure, which is the key variable, a very key variable, we don't have an apparatus that spans, for example, a really critical range, like 20 to 30 or 20 to 40 gigapascals. If I had an unlimited research budget, I would try to have such an apparatus.
Yep.
Like the Sinter, I would like live in Japan.
Just speak
Is it
loudly.
known where these elements sit inside a polycrystal material? Are they on grain boundaries?
Yes. Do you want to know?
Yeah.
The osmium, iridium, ruthenium group in the mantle tend to sit in alloys and and a mineral like laurite sulfides certainly. So they're mostly in alloys and sulfides. They're usually divided into two groups based on what types of sulfides they like to go into. So platinum and palladium tend to go into base metal sulfides. And that's why they behave so differently during mantle melting conditions. So osmium, iridium, and ruthenium are typically really compatible during the production of basalts. So they are highly fractionated in crustal production. But they're really trace phases, so it's hard to locate them and hard to document them. Yep?
Rich, so put the question differently, I guess one way to ask is, doing this type of experiment, is it even on the right track?
Yes. Next question. What do you mean on the right track?
So, if the nature really provides late accretion materials through that kind of thing, then the partition experiment became irrelevant.
Well, I
explained by late accretion.
Yeah, I think the answer to that is it is relevant, and I think it's relevant because of what I've been saying, which is if you can explain, if moderately siderophile elements were set by that process, and therefore there was metal silicate partitioning of all the siderophile elements under those conditions, and if the partitioning of elements like palladium is accurately defined by the experiments, then we're missing something, because you can't have late accretion yet an excess of palladium resulting from magma ocean processes. For late accretion to really work without a perturbance of the chondritic relative abundances, you have to end up with a mantle with sufficiently sub-primitive mantle abundances that adding material on from a chondritic source just buffers the concentrations up. So I think we genuinely do have a problem, and it's telling us something. I just don't know what it's telling us at this point. Okay, we're going to have to end shortly, but go ahead.
Okay, so you said that Mars was strikingly close to Earth, but the pressures would be much lower.
Yeah.
Presumably the temperatures would as well. What does that tell you about this whole?
Well, it's a problem from any of the model standpoints. It's a problem from a magma ocean standpoint, but it's also a problem from a late accretion standpoint.
You have to add the same stuff.
In the same proportions. Yep.
What's the assumption about the mantle that's below the magma ocean? What does that hold?
Yeah, well, that's a good answer. I think the assumption is that that would start off with very low abundances and ultimately get mixed back in, and therefore diluted the perhaps somewhat higher abundances that you may have had result from the magma ocean process. But
does it affect the choices of F, for example?
It would. It would. I think it has a bigger problem on absolute abundances, though, than relative abundances. And I personally favor the relative abundance arguments over the absolute because we have two isotopic tracers for that. I think we should end the tutorial and move on.
One more question. What about the possibility that siderophile elements are still being exchanged between the core and the mantle today?
That's another story.
Just something to think about.
That's another tutorial. Okay. Who's got the follow-up talk? We have a talk. Alan. Right.